And these are the favorite questions from this topic that the examiner wants to ask from you. They just change the diameter of the wire and they ask you to comment on the drift speed. They can ask you for the ratios, or they can ask you to draw the graph. Sometimes they can ask you to find the drift speed at the other point. Sometimes they ask you to find the ratios. And the trickiest case would have been if they asked you to draw the graph, which is not tricky indeed. If you're able to find the values, it's not tricky. It may just look tricky. So where do we start it from? Well, it's pretty simple. That we need to draw the graph, and the question is for 2 marks. So at least you have to choose 3 points on the x-axis, and you have to plot 3 points, which means you have to find the drift speed at 3 different positions. Well, we know the drift speed at the point S, at the position S, when the diameter is d. What is the drift speed? It is Vs, V sub S. So that makes the things easy for us. So when the position was S, the diameter was d, the drift speed was S, Vs, sorry. So this is the very first point over here. So we have marked the first point. And matter of fact, another point is very easy uh, for you to find, which is the last one. When the diameter of the wire increases to 2d, which means they have double the diameter, now the drift speed has to decrease. According to what we have studied in the theory, if the diameter increases, the drift speed decreases, because increasing the diameter increases the cross-sectional area. Now the quick question is, if the diameter is increased by a factor of 2, okay, the diameter is doubled. So the drift speed would decrease by a factor of what? Would it be Vs over 2? Would the drift speed be reduced to half? Would it be V over 4? Would it be Vs as it is? Ramin, could you answer that?
V over 4.
V over 4, very good. So the drift speed would be decreased by a square of this number. If they increase the diameter 3 times, the drift velocity would have been Vs over 9. So it won't be this one. It won't be this one. It doesn't stay the same. It would be Vs over 4. So it would be reduced to 4 times. So what is that point? The first one was Vs. So Vs over 4 would be 0.25 Vs, which is a point that lies somewhere over here. Over here. Now we just need one more point. So we could know if the graph is a curve, if the graph is a straight line, or if it is a curve, then what is the gradient? What kind of gradient? Increasing, decreasing, whatsoever. So what I'm going to do is I'm going to choose a point in the middle, the easiest point. So I'm going to choose a point in the middle, which is, let's say, over here. Let's use this point, which is exactly in the middle of S and T. If the diameter is d at S, and if the diameter is 2d at T, then what would be the diameter in the middle? So at S you can call it 1d, just for sake of convenience, for your convenience. If the diameter is 1d at S and 2d at T, what would be the diameter in the middle? Manur.
1.5.
Thank you, that's the right answer. 1.5 times d. So 1.5 d. Now what happens to the drift speed? Well, the easiest way you can calculate is once again that the drift speed would decrease by square of this factor. So whatever the drift speed was, it was initially Vs, it would now be reduced to 1.5 square. Just like it happened over here, the diameter was 2d and drift speed decreased by a factor of uh, the square of this number. So what you have to do is you have to find the new drift speed, which would be 1 over 1.5 square of it, which is 0.44. Sorry?
0.44.
Yes, so it is 0.44 times of Vs. So when the diameter was 1.5d, the drift speed was 0.44 times of the original drift speed. 0.44. So all you have to do, just find the point 0.44 and we can just mark it over there. So the middle point, that is slightly problematic. Otherwise, it's just very simple. So this is the central part. So our point would be somewhere on this line, but how much on the y-axis? 0.44. So all we got to do is we need to find where do we plot 0.44. Okay, so one of the way is you simply use the traditional approach. You count the boxes. You can probably see what is the separation, or the formula is, if you don't want to count the boxes, so there is a formula as well. The formula is point, which you need to find that where would this point be located. So that point minus starting value, like where does that axis start from? Like for this one, the axis start from 0, divided by the scale factor, divided by SF. Not Street Fighter, but scale factor. Now what is scale factor? Scale factor is division. Scale factor is what does a small square represent. So for example, 10 small squares make up 0.25. So one small square would make up 0.25 divided by 10, which is 0.025. So one small square would make up 0.025. That is your SF. So what is the point that we want to find out? The location of the point, it was 0.44. The starting point of the axis is 0, divided by the scale factor is 0.025. You hit it on the calculator and you'll get the number of the block, small square, where this point should be plotted. So just let me hit it on the calculator. 0.44 divided by 0.025. So we get 17.6. So in between the point, in between the block 16, sorry, in between the block 17 and 18, small square. Okay, so 10 blocks here, this is 15, and if I zoom it in, 15, and then you have 16, then you have 17, Over here you have 18, and in the middle of it you have 17 and a half. So now, as you have plotted at least 3 points, and if you see the trend of the points, you can safely say that the graph is, first of all, not a straight line. It would be a curve, and you simply have to join the 3 points with a freehand curve. Just join the 3 points with a freehand curve and you'll be getting the desired answer. So I may not be able to join properly this, okay? So there's a little bit of bending in that, but it would be a it would be a smooth curve, okay? You have to draw a smooth curve. For me, it's like slightly difficult to draw, but when you draw it on the sheet of paper, it would be a smooth curve. Okay, so this one question is done. Let me open up the questions from the workbook now. The questions that would be there on your workbook. And the answer for the first one, we explained this question already. I equals to NaVQ. Q could be the charge on the electron. If it is the charge on an electron, we can represent it by E as well. So the formula can also be written as NaQe. So it's just the same thing. And which statement was not used for the derivation of this equation? The answer is simply option C. Because this formula reads number, capital N, equals to number density, small n, times area, which is incorrect. The actual formula was number equals to number density times volume, because we said this thing, number density equals to number of charge carriers per unit volume. So it was volume over here, not the area. That was a problematic part in this one. Let's take a look at the next question. So we need to find what is the current in the wire. Well, we do have the value for the current. We do have the expression by which we can find the current, which was I equals to NaQe. Sorry, NaVe. NaVe. This is the expression that is used to find the value of current when the drift speed is given. So I needs to be found out. The value of the length is 12 centimeter, aka 0.12 meters. 5.18 to 10 to the power 22. This is the value for number of free electrons. It is not the value of small n. The small n is number density. But this is the value of capital N, number of electrons. And this is the drift speed, which is given as, which we write it as V. And the charge on the electron we know already, 1.60. We open up the paper, page number 2 of the question paper, and we take a look at the data sheet. The value of E is written over there. And this value is cited as charge of the elementary charge. So I equals to, now you see this thing, small n. We are not provided with the value of small n. So we can rearrange, or we can insert the value, insert the expression for small n, which is capital N divided by V. Because charge density equals number of charges per unit volume times A times V times E as it is. What do we do then? I equals N. Instead of V, we can translate it into the product of area and length. Because if this is a conductor, which is kind of a cylinder, and the cross section area is A. This cross section area is A, and the total length is L. So the volume of the conductor, because it is a cylinder, which is a kind of a prism, and the formula for volume of any prism is cross section area times length of the prism. So a cylinder is also a prism, which we call a circular prism, times A as it is, times V as it is, times E as it is. What do you do afterwards? It's just trivial to find the value of I. So you can just cancel A with A. The value of N is given. The value of small v is given. The value of E can be seen from the data sheet. The value of L in SI units is 0.12. And what do we do now? We hit it on the calculator. So here we have this one. Fraction, and then 5.1 into 10 raised power, how much is that? 22. 10 raised power 22 times V is, make sure you're not writing everything else in exponent. So V is 4 into 10 raised power -6. Okay. And E is 1.6. So this thing times 1.6 into 10 raised power -19 divided by 0.12. And we get 0.272. So we get C as the right answer for this one. If you are clear with this, then I'll move on to the next one. All right, so here we have the next one. A very easy question we have. If you know the shortcuts, if you know the ratio method of the drift speed, we have done this question already. We'll go through it very quickly. So the diameter on this side, on the left side, is D. Okay, so the diameter is D, and let's say the drift speed is V. Okay, let's not be very specific. Let's keep the things general. And on the other side, the diameter is increased by a factor of 2. So the drift speed would be decreased by a square of that factor. So whatever the square of that number is, that would go in the denominator, and that would be your new drift speed. So what is the drift speed at V? At P, it was V, because we need to find this ratio. So let us insert the values in this expression. So it would be drift speed at P was V divided by drift speed at Q was V over 4. Then you do keep change flip. VV cancelled out. You're left with 4. So D is the answer for this one. So let's take a look at the next one. A slice of germanium has which is a semiconductor, has a cross section area of 1 centimeter square, and we have to convert 1 centimeter square into meter square because we'll be needing it anyway. So 1 centimeter square, keep it in your mind, centimeter to meter, we just multiply by 10 to the power -2, or we simply divide it by 100. But for centimeter square to meter square, we divide it by 10,000, or we multiply by 10 to the power minus 4. And for cubic centimeter to cubic meters, we multiply by 10 to the power minus 6, or we divide by 1 million. So these are the conversions that we use. So this thing, the first one, can simply be written as 1 into 10 raised power minus 4. 1 into 10 raised power minus 4 meter square. The current can be written as 56 into 10 raised power minus 6 amperes. We can get rid of that prefix as well. What else do we have? The charge number density of the charge carrier in the germanium is 2.0 into 10 to the power 13 cubic per cubic centimeter. This is the value of N. What is the average drift speed? So if I rearrange the expression, I equals to NAVE, because we need to find the drift speed, so there would be V equals to I over NAE. And the value of I is very simple, 56 into 10 to the power minus 6 divided by the value of N. Okay, we insert the value of N in a moment. The value of A is 1 into 10 to the power minus 4. The value of small e, it is 1.6 into 10 to the power minus 19 coulombs. And the value of number density, charge carriers number density, this thing. So we have to convert it into 2.0 into 10 to the power 13 from per cubic centimeter. You have to convert it into per cubic meters. Now let me ask you the question. Ramin beta, how do we convert per cubic meters to per cubic centimeters to per cubic meters? What do I multiply this number with?
10 raised to the power minus 6.
Okay, so this is what most of us would be tempted to say, that we want to convert centimeter cube per cubic centimeter to per cubic meters. We multiply by 10 raised power minus 6. But you need to realize one thing, that you're not converting cubic centimeters to meters to cubic meters. Rather, you're converting per cubic centimeters to per cubic meters. So you have to multiply by this number, but you have to multiply this number by this factor in the denominator. Or if you want to simply multiply it, so you have to write 10 raised power not negative 6. You have to write 10 raised power plus 6. So you can just look at it in two different ways. If you were converting cubic centimeters to cubic meters, you would have been multiplying by 10 to the power minus 6. But since you're converting per cubic centimeters to per cubic meters, you just reverse this sign of the exponent. Ramin, you want to add something?
No, sir.
Okay. So you see, whatever way you're comfortable with, so the conversion of per cubic centimeter is tricky. Likewise, it's not only limited to this thing. For example, let's say, let me write over here. If you have to convert per centimeter square to per meter square, what do? Let's say the value is 5. 5 per centimeter square. You need to convert it to per meter square. So you don't multiply by 10 to the power negative 4. Rather, you multiply by 10 raised power plus 4. because this would have been from centimeter square to meter square, and this one is for per centimeter square to per meter square. So even if you think you're very good with the conversion, this is a part that you're very likely to commit a mistake. So this one would be once again 2.0 into 10 raised power 13 times 10 raised power not negative 6. If you want to write negative 6, write it in the denominator. Or here you can simply write plus 6. What do you do afterwards? You open up the calculator and insert the fraction 56 into 10 raised power negative 6. Which in 2SF you can round it off to 0.18. So let's move on to the next question, which is also related to the drift speed. We have this thing: state what is meant by the symbols A and Q. So A is a cross section area, and small n stand for number density of the charge carriers. Now once again we have a question related to the graph, and in this one we have to start from the point X. We have to go towards the point Y where the diameter is being decreased, and we have to choose, like I said, for 2 marks you have to choose at least 2 points, and then you have to plot the graph accordingly. Sorry, not 2, rather you have to choose at least 3 points. So I'm going to go through this one quite quickly. So for example, the drift speed at the end X is Vx, V sub X, where the diameter is D. If the diameter is being decreased by a factor of 2, the drift speed would be increased by the square of that factor. So the square of 2 is 4, and the new drift speed at the point X would be, at the point 5 would be 4x. Then we have to look for the point in the middle, for the position that is exactly in the middle, which is at a diameter of, so just take a look at that. The diameter over here is D, which is 1D, and the diameter over there is 0.5D, because 1 over D would be 0.5D. So what is going to be the diameter exactly at the middle? Exactly at the middle, it would be 0.75D. So how do you find the drift speed at this point? Just, if you're not comfortable with the ratios, just use the formula. Otherwise, if this is a factor behind the diameter, divide the drift speed by square of this factor. So 0.75 square. 1 divided by 0.75 and square of it is 1.77. It is a recurring number, so 1.77 can be rounded off to 1.8. So the drift speed in the middle would be 1.8 times Vx. Okay, and matter of fact, at the position Y, we have done the same thing. You see the diameter, if I write the diameter in fraction, not in fraction but in decimal number, it would be 0.5D. So the drift speed would be divided by the square of this factor, the square of 0.5. So Vx divided by square of 0.5. So what do you get? You can just check it out. 1 divided by 0.5 square, and that equals to 4. So you get the same answer either way. So what points do we have? We have 1, then we have 1.8, then we have 4. So the first one at x was 1, which is Vx, at 5 was 4, and then we were having 1.8. So this one is quite easy because you have 10 blocks. One small square is representing 0.1. So 1.1, 1.2, 1.3, 1.4. Over here you have 1.5, 1.6, 1.7, 1.8 over here. Then you join them with a freehand curve, which would be slightly difficult for me, but on the sheet of paper should not be difficult for you. So something like this. Make sure you're just connecting the points smoothly. That's it. So let's move on to the next one. Here we have the next sample question. Two lamps P and Q are connected in series to a battery as shown in figure 6.1. The radius of the filament wire of the lamp P is twice the radius of the filament wire of the lamp Q. The wires are made up of the same metals, of the metal with the same value of N. So the charge carrier's density, number density is same. We need to find the ratio of the drift speed of the filament wire of P divided by to the filament wire Q. Okay, so if I draw the diagram for your convenience, it will look something like this. Side P here, side Q here. Okay, so the radius of this thing was twice. Let's say the radius was 2r here, and over here the radius is being decreased to r. Then you need to find the ratio of the drift speed. So whether it be radius, whether it be diameter, the ratio wise it would exactly be the same thing. Like I showed you the formulas over here at the start of the lesson. Okay, I think I've cleared those formula. But whether it be radius, whether it be diameter, it won't make any difference. You have to take the ratio of the squares of the radius. That's the rule of thumb. So for example, let's say the drift speed over here was V. Okay, the drift speed on the side P was V. What would be the drift speed on the side Q? So on the side Q, because the radius is being reduced to half, the radius is being decreased by a factor of 2. So the drift speed would increase by a factor of 4. So the drift speed over here would be 4v. This is the simplest working. If you want to save most of your time, the shortest way to answer this question is this one. Or if you're not comfortable with this, you always have the method of using the formula. So this is your R1, this is your R2, this is your V1, which is V, and V2 needs to be found out. And what is the formula? V1 over V2 equals to R2 square divided by R1 square. What is V1? We assume that V1 is V. What is V2? Well, V2 we don't know. We can simply write x over here. We don't know the value of V2. Or let's just write V2. We need to find the drift speed at the Q. So V2 is the drift speed at the end Q. What else do we have? R2, which is the second radius, it is r square because the second radius is r. What is the first radius? Because the radius at P was twice, so it is 2r. So the square of 2r would be 4r square. This thing cancelled out. So what is the ratio of the drift speed? What is V representing? The drift speed at P. What is V2 representing? The drift speed at Q. So what is their ratio equals to? The ratio equals to 1 over 4. So the answer to this one would be 1 over 4 or 0.25, which is the same as this one because the drift speed you have calculated at Q. Drift speed, let's say at Q is 4V, and the drift speed at P, let's call it drift speed at P equals to V. Then if you find the ratio, V sub P over V sub Q would equal V divided by 4V. If you insert their respective values, for example, this value goes over here, this value goes over here, V and V cancelled out. What are you left with? 1 over 4, which is 0.25. Then we have the last one, the theoretical question. Wire X and wire Y have the same cross-section area. Okay, so X has the same cross-section area as the wire Y. It is made up of same material. Wire Y is longer. So let's say this is a wire X and this is a wire Y. It is longer than the previous one. They have the same cross-section area. So we get rid of the wire X and we connect the wire Y in the circuit. So we get rid of this one and we connect this one. Assume that they have the same temperature, they have the same cross-section area, they are made up of the same metal, means they have the same number density, charge carrier's number density. If they are made up of the same metal, Steiner explained whether the average drift speed of the free electrons in wire Y is greater than or same or less than that in wire X. So we need to comment on the drift speed. So I'm going to write down the formula of drift speed. V equals to I over NAVE. Sorry, V we have already placed over there. So you don't have to write V once again. So this is what we get. Now you see many of the values being kept constant. For example, current. Okay, charge carriers number density would be same because it is made up of same metal. So the number of charges per unit volume would be same. Same cross-section area is given over here. What else do we have? The charge on an electron, it's just a constant number. It can't be changed. It is 1.60 into 10 to the power negative 19 coulombs. So what are we left with? Current. Now current depends on the resistance as well. And if you're able to recall, because I'll explain this topic in this chapter as well, the effect, the dependence or the factors that affect the resistance. But you should be able to recall that if you increase the length of the conductor, the resistance also increases and thereby the current passing through it would decrease. So if the value of current decreases and everything else is constant, so you can say drift speed would be proportional to current. And if the value of current decreases, the drift speed would also decrease. And why does the current decrease? Because the increasing the length increases the resistance, and increasing the resistance decreases the current. So this is how we answer this question.